My name is Philipp Ahmann. I will present today about the telltale mysteries. So it gives you some insights into ELISA, the ELISA project, how we make use of the AGL instrument cluster, and how this all fits into the functional safety hollow. So I guess if you've seen the abstract which I prepared for the talk, there have been some nice buzzwords included. So there were things mentioned like we have a quick start for engineers, we use certain tools for workload tracing, we modify whatever's in there, like the kernel configuration, enhance with additional apps, and put this all onto QEMU image. As we want to have control, so I guess we have a good fit to what Jan Simon has also just before presented about reproducible builds, and maybe I get another reproducibility factor also in here. The SBOM generation, also something which we covered, and so for this also fits to upcoming work packages. What I like is if you are in a way on a hollow going for a new adventure, typically it's always good to have a little bit to write in there, so we will look into some field notes from the past, some field notes from the upcoming work, and while we go through the slides, we will filling this field notes book step by step. So let's take a look at such field notes and open them. What you often see in the beginning is that there is an owner which would like to see to whom does this book belong to. And as already mentioned, I'm Philipp Ahmann. I'm currently assigned to a project which focuses on embedded IoT Linux, where we try to bring in different Bosch departments closer to open source work, interconnect them, because we see there's so much commonality around many divisions. And today I am here mainly speaking for the ELISA project. I'm the technical steering committee chair there. I am also leading the automotive and systems work group. And this basically is fed by the many years experience which I bring. I'm a personal Linux user since many years. I started with Ubuntu 6.10, I guess, so I know many of you may have been even longer with it. I used this when I was an exchange student, and we set up old deprecated hardware, and at this time a lot of exchange students didn't have their own PCs, couldn't bring it to abroad, so therefore we were using old outsourced university PCs and put a fresh Linux on it, and it has enabled a lot of engineers and students to start working from home and doing the work. Don't need to go for every search to the university. In automotive, Bosch started more than 10 years back on it. I did as well. We brought a 2.6 kernel into an infotainment system at this time and still producing parts of it. The apparatus, which is labeled there, is Debian-based distribution, which Bosch works on together also with Collabra, and where we try to widen this also for wider industry. Right. I don't know who has been to the Open Source Summit Japan. A few hands, that's great. I'll make one page also from my field notes from the Open Source Summit Japan. I had a talk there on the elements towards functional safety, so it was giving an insight about how much Linux is used, how the different ECUs come together, that it's growing complexity, what are elements to resolve this complexity. Also there, the telltales were of course mentioned because it's our entry point, and if you later on want to browse through, there's the link to the slides and also to the recording. Short remark, there is a silence at the beginning of the recording because I missed to switch on the microphone. Right. Already there was an idea on the step-by-step approach and the increased responsibility, and this will be also something which comes up in this talk. After this, we had a short session from ELISA at the FOSDEM. This was more the bright overview, and normally I have a quick intro on what ELISA is. In my slide deck today, I skipped it. So if you want to see all the things on the different work groups, what they do in more detail, just check out the FOSDEM part. And I guess now it's good time to just see what we all want to do during this adventure. So as we could see from the book, we have different topics to cover. So what we will need as our equipment is the instrument cluster demo, which basically comes from the AGL part, as we know how hard it is to get certain hardware and we want to make things accessible. We're using a QEMU image on this, and people would like to use this, and we need to make sure if someone grabs up things, it needs to go into a CI. As this is nothing which is specific to the work of ELISA or bringing safety elements, safety mechanisms in there, we also enhance this with a safety monitoring app. This also fits well into the concepts of Yamaguchi-san, who has also shown that there is a safety monitoring island, and depending on what you do, you will give more responsibility to your safety monitor or less. And we try to give as less as possible responsibility and mainly use this safety mechanism part as a watchdog and put a lot of functionality from a safety monitoring app also in the Linux system. And this means you need to understand the system very well. So for this, it's always good to see what is involved in this. And for this, we have workload tracing. So then let's start maybe with the instrument cluster. Instrument clusters from the past were very mechanical dashboards. So if you look in old sports car or overall old cars, you see these LEDs in there or even light bulbs which have been in there in the past. And nowadays, as we have more and more software involvement, the cars look fancy, and if you don't want to go for the vintage style, you most likely come up with large areas of screens. And in this use case, there is no real fit anymore for a LED light bulb roundish kind of thing. You may survive with having some rendered part, very simple, but it's even increasing that a lot of animations come in. You can customize colors and whatever you could consider. So greetings to software-defined vehicle, right, which also would try to find to get a smartphone on wheels or whatever. And why we have selected this use case is because it shows wonderful how suddenly this mechanical parts turn into software becoming prominent, and this is often implemented in a commercial RTOS. So you come up with additional license fees, additional things, and at some point of time you reach the boundaries of an RTOS and would like to enhance features with a rich, strong, large OS like Linux. And therefore we use this use case on the one hand because there is an existing implementation from AGL, so thanks a lot for this, and also because it is good to derive requirements. Another thing which we figured out was we started also discussing about driving assistance use cases, and if you go in this discussion, people start to say, you can do an architecture like this, the system could look like this, and we start talking about the system architecture a lot before we reach the problem or the challenges which we would like to tackle with the operating system. And the telltale warning sign is a very simple use case. So for this, you just need to understand there is a light bulb and it goes on if there's a warning, like a check engine oil pressure, and most of you have seen this before, know when you switch on the ignition you see these things. So this was a good set where we came up to drive the requirements on this, and as explained, we had the path of it, we have today's displays, and what's also very nice about this, which will come, is that there is no strong actuator sensor involvement also, so which gives it much easier chances to bring this onto a system or a QEMU image that you can download and experience it and try out. So even if you have no experience on a hardware, you can still start analysis on the kernel level. Right, and then on top, I could explain it quite fast to you what a telltale is, so I said I mentioned this one, but it's just the basic challenge for more complex use cases, because if you see that in telltales you compare memory regions, image data, and so on, you can also consider what happens if I add real time, what happens if I do camera addition, if I have other sensors and actuators, and by this you can grow. And if you don't feel comfortable to have everything in a Linux domain, you can just put workloads also into the RTOS and say, what of the RTOS can I offload, what can I bring in, and this enables you a good start. And this would be all nothing if you don't have a demo implementation. So we definitely need a demo for it. And as I said, it's on Needlefish, so we have the Needlefish based instrument cluster. at the Meta ELISA layer. I have QR code for this one, which you can just simply check. So there's basically an instruction in there what to do. And we needed this, or we started with this Meta ELISA in the ELISA Tech because it enhances the AGL instrument cluster demo with new functionality. What we, for example, did was we added the safety app and the watchdog functionality. I explicitly marked this as a mock, so it's nothing used in production. Also, the checking mechanism of Telltale will get improved. And as we started on this activity, we were considering what else can you do. So we also trimmed down the kernel configuration because there were a lot of modules which we didn't need for the instrument cluster. So we trimmed this part down. We may trim down further also for additional packages which are in there because a lot of things we don't need for the primary use case, and we try to get rid of side effects as much as possible. And also put this as an element so that you can consider stripping things down. And when we all started in this group, we needed to learn what will we do, how do we do it. Then someone comes up and say, okay, I would like to start my interaction. I have another PC, so we have written down step-by-step build instructions so that even if you're a newbie and may go then from the Meta ELISA also to the workgroup automotive description, you'll see a step-by-step guide, including even how to do a git commit. So it's really going down from the beginner. And we also checked the call of the QEMU image, put this in there to see that you know which parameters to call, which are mandatory, which not, what is the necessary things, what are the effects if you turn off virtualization, and so on. And yeah, even if we had this, there was this guy coming up, well, I'm using OpenSUSE Tumbleweed, and suddenly it does not comply to the Ubuntu which you have used, or the Debian one which has been used at another place. So a Docker file for easier reproduction really makes sense. Right. The main addition, which you can see from the original demo, is this little danger sign. So there's not much more than this from the first visibility. But for us, it was very important to have this also based on a regular build environment in a reproducible form. And we try to use the steps which we have in the how-to as close as possible, also with the scripts we use, the scripts getting called from the CI, so that the CI in the end does what a user would do or a developer would do. And yeah, what we have set up, we were mainly using GitHub originally, but if you put up the GitHub actions and so on, there are certain risks if you have involvement of external servers, and we thought that GitLab was giving a better fit for us there. So we used GitLab, which currently then interacts with GitHub pull requests on demand or on a regular nightly base. And what we also figured out over time is that things can go wrong. So we're using also the OpenQA. There was a presentation yesterday on the OpenQA parts. We have this comparison image. We check that our danger sign is also properly displayed. And we actually also hit a bug there, or not a bug, but a change with 14.03. There have been some modification which made life easier for AGL usage. And we had to rewrite a few lines of code. So that was good, and we directly saw this at the day when the release came out. We pulled the latest release in our CI and could file a bug on this. Also, this CI helps to create the container image. And just now, I guess next days we will have not only the Docker file, but really the container image there for download. And what we also do is we provide the QEMU image there. So this gets all together in a reproducible form. Let me see if I forgot something. Yeah, here's again the quite similar URL. It's a different one with the Meta ELISA CI and now in GitLab rather than GitHub. I was talking about the guarantees of the robustness and that we had the issue. We covered this. It's really built on a daily basis, so every day. And maybe important thing is whenever you get a link to a previous generated image, we're just keeping our image, the QEmage, one day. Whenever the new build is there, the old artifacts get deleted and you cannot download the artifacts anymore. And by this, we want to make sure that you don't have a choice on too many and may go to different versions, so we can just go there, but we can still reproduce whatever we have done on the state. Right. Yeah. What I missed to mention was that we also have shared state, so we just switched it on our servers. I guess we could also use the AGL one, but as we also have our parts in there with the Meta ELISA, that went into this part. Yeah. And next question is, what do you really do? How do you interact with the demo? So now you have understood there is the Meta ELISA, you have followed the instruction, took the Docker file, figured out more. Maybe I start with a QEMU directly. Let's check what the safety monitoring app is actually doing. So there is the top left corner, which you can see, there is our control panel, and basically the idea which we had was we use a named pipe in our normal flow, and this interacts with the Kuxa cannon signal. You can drop messages, and we would like to use this safety monitoring app to test our mechanisms. So we can hook into the elements, and we can corrupt messages which can request, or we can drop messages, and also just trigger the safe state. For those which are not aware of this, so for the safe state trigger means whenever a failure is detected, your system should come into a state where you're safe in the operation. It could be that you stop a car, for example, if you're in an autonomous driver's condition, or so you would just stop, you switch something off. Of course, sometimes this is not really convenient, but on the other hand, for example, if you have an instrument cluster and we detect that something goes wrong, you can simply switch the display off, and if you see that your instrument cluster is not showing anymore, you definitely know that something is wrong and you may need to restart. We just use this as a mechanism, and and this is all done by a watchdog, because the worst thing you don't have full control on your scheduler on the Linux system. It runs very stable, and I was running basically the Nextcloud instance, a smaller one at home, more than a year without a restart. So you can see that it runs quite long, stable, and I had never issues, but still you need to have a monitor in there. And it's not that this app call is there to really be used in later, it's really a test implementation to see that the mechanisms work, and with the command line interfaces helps a lot for just better interaction than rather directly going and writing to the pipe. Right. The call is then quite easy. It's also mentioned in the documentation. It's signal source control panel. You see it basically here, that where it comes on, and this is the larger part of this demo, and well, it's a continuously running one, so we'll see soon again how the different effects are done. There's a video link in the PowerPoint PDF version on the SCAD, so you can use this. And as I mentioned it a few times, there is this watchdog. We use this approach, and it's really commonly used in a lot of areas in automotive and other industries, that you have watchdog mechanisms to control what you're doing. So I made this drawing in the top left where you can see you always have an intended functionality, and you should your design in a way that the functionality will work every time. And then you need to see that you monitor whatever happens there, that you guarantee whatever is rendered will be there, and that you can take action when something goes wrong. That's also what you could, for example, imagine comparing the image content. But in a Linux system, it's getting more complicated, because you need to make sure that it's rendered in a specific time, checked in a specific time value, so comparing memory region A with memory region B in a specific time. And here comes an external watchdog which would have the chance to restart the system or to switch something off, to kill basically what you're doing. Remark, this will not hold if you are in an autonomous driving level 4 use case where you are on the highway and then there would just be the watchdog and switch off the system. You would take other mechanisms in there. Yeah. But the eGAS approach, I linked the PDF there. That's German and an English version of it. It describes quite well that you need to have a watchdog, and that the watchdog needs a bit more intelligence. So it's a challenge response watchdog which we have, which means you send something like a little riddle, like a little request, something which gives an option to answer, because it could also be that you're answering petting requests which say, I'm still alive, I'm still alive, I'm still alive, I'm still alive. hangs in a loop and will just send this message. So the watchdog say, give me the answer for what's 1 + 1. And therefore you do a little bit of intelligence. You can use your creativity to get something out of it. And yeah, this is used in many industries. And by this, even if you go for architectures where you involve later on hypervisor, if you go on a wider set, I guess you will always find still a watchdog. And you will just use it as it's not an expensive one if you think about the life of people and the causation of accidents. And you can use also an RTOS, as I said, to have a monitoring of the system. We discussed it yesterday in the instrument cluster BUF, where you could, for example, also just say, well, I don't give the responsibility yet to the Linux system, but I'm doing all this telltale rendering comparison, and next to it there is my monitoring observation still in the RTOS, and this has a chance to take over. This would be also kind of a watchdog mechanism, and by this you can just take things away from the RTOS until you really end up with just something which watches it and notifies and gives control. Yeah, I guess I also partially cover this. It does not release you from understanding the Linux system underneath. Because what I heard a lot is when people ask about ELISA, they come and say, oh, when will you have a safe Linux? How can I use it? And if you start talking to a few of these people, they're neither Linux expert, not safety expert, but they suddenly want to make a safety-related function with Linux. And this is something which you will not be capable of, because you need to understand the system, this Linux system, and how it operates in the context, what is other workload, what could go wrong, how does your real system environment looks like. And therefore, this is important. It's just a helping mechanism, but it's also a lot of responsibility for those who are preparing things. And if you do the right things, your watchdog will never be used. And this should be really the statement which you take away. You need this watchdog. It's your ultimate safety net if something goes wrong, but you would always design your system that you don't need the watchdog. The watchdog is just the last thing which would trigger, and it's even if it's not safety related, I guess if you're running a car, if the frame rate drops, you will not be happy. If the display flickers, if assistants don't work, whatever function, as soon as something does not work as expected, it's user convenience. And if you build a product, the customer will complain. Right. Yeah, and if we see this understanding the Linux system sufficiently, we thought that it's getting quite complex to see what is really involved in there. And we have another work group within ELISA, which is dealing with medical devices use cases. And they started with an open APS. This open APS basically is an open or artificial pancreas system, an insulin pump built on a Raspberry Pi, and it was created without a large safety analysis. It was just built by users in open source without safety standards. And what the work group did was they looked into the architecture, they were drawing diagrams, did a system analysis, and at some point they figured out, if I want to go deeper, I cannot really handle it anymore. So they came up and using S-Trace C-Scope, they used StressNG and other tools to generate workload. And this is the nice thing, recently also was added to the kernel documentation, so we were quite happy that it was taken. And we will enhance it further and also use it now in the automotive workgroup to do our tracing there. What we would like to see is that we have system calls, how often these calls, so what are the main triggered calls, which subsystems of the Linux kernel are actually involved, so that we get a much better understanding on how our architecture looks like, how we entry different subsystems and calls. And what we also learned, it's also about what you don't see, right? Because there are much more APIs, there's much more involved, and you may wonder, am I really using the right things, what I'm not using? And for this, we have certain extensions with the call tree and KSNF, its own developed tools, which basically does a graphical representation of various kernel calls and so on. It can take generated kernel images and just create a graphical representation of subsystem calls in there. It looks very messy, but it can help you to see what's left and right of your actual calls. Yeah. We also wanted to give a try with system tab because it gives you ideas on the process, how things are called. It's more interactive than just having statistics, so you can see how calls go. and that's something which comes next. Yeah, and I guess if we shortly flip back to our beginning where we looked at, so we had the instrument cluster demo covered, the QEMO image was mentioned on the Meteor ELISA CI part, monitoring app with the Ncurses demo part, the watchdog, and the workload tracing. So we can outreach to next steps, which would be, from our perspective, to get a connection. We have a lot of documentation around this system analysis, which was written down in diagrams and again and again. And we said we would like to trace the workload, and by this also improve the safety monitoring app, because as written earlier, it was a mock, and this mock does not really compare image data. And if we want to do proper workload tracing and see which subsystems are involved, we need to interact with the graphics library, with the frame buffer, and do image comparison to have this tracing over there. So therefore, we will improve the safety monitoring app. And then when we have done the tracing, we also have a kernel analysis, which goes back into the design patterns, the design architectural diagrams. Then we saw that if I explain, even if I have a simply explainable use case with the telltales, people come and ask me for these new fancy architectures which have hypervisor involvement, RTOS involvement, all go into, in best case, you also add the container, you have all things together, and then you use it for driver assistance. And by this, we want to use the current momentum which we see in the AGL movement, which we see from external, that we also bring up the demo into this multi-domain system. We have some prototyping work in the systems work group. This will come on the next page, so I'll explain more about this. And Simon mentioned this, the SBOM generation. I guess we also triggered the SPDX pretty format brought it to Joshua and said, could you add this and backport it? So that we now have it rippled through also with the AGL release taken up, and now we will also have an SPDX pretty format. We're also considering SBOM generation for safety-related functionality. So there's the SPDX special interest group for safety, so that this traceability aspect gets a stronger notion. So it's meeting every Friday, unpleasant time for Asia and also for Europe at 6 p.m. in the afternoon, European time. So, but people couldn't find a better slot so far. But summaries are there, and if you have interest in learning more about the SPDX FUSA special interest group, just reach out to me later on. Right. What we also wanted to do, I may teased this at the beginning, is we will reduce the image size by just throwing out packages and things which we don't need, so that we really get to a minimal instrument cluster. This goes with a safety philosophy that you shouldn't carry things around which you don't need. It doesn't work with a platform approach where you try to cover as many use cases as possible, but with this one you can just see that you concentrate on things and show this you don't really need. Look only on the things you really have to do. Yeah, everything which we have is tracked logged in the workgroup automotive GitHub repo, and we run through this every week. So we always look for new people to join. I guess by this I'm grabbing the OpenQA part also in there and saying contributions are welcome, bugs are welcome, everything which enhances this is nice to see. And yeah, as mentioned, for the multi-domain system, there's a more complex drawing in here. We have already, based on a demo from Xen, from Stefano Stabilini, did something last year in June. We derived this demo, which was on QEMO, and put it on a Renesas RCAR H3. We ended up with a little bit of confusion and handling of graphics driver binaries, where we are not yet through to see how can we distribute them properly. So again, here we may fall back to a QEMO-based demo. We also set up a Xen system with the AGL in there, and we are now in a process to having AGL infotainment, AGL cluster together with Xen and Zephyr as an RTOS. And in these discussions, like Richard Puri is also quite often available for the Yocto parts of it. We have Stefano Stabilini in there, a few guys from EPAM joining regularly, so that we just bring this forward in a demo case. Yeah, Sapphire is also involved there recently, and I guess by this I had this mentioned. Yeah, And yeah, this I didn't mention yet. We have the step-by-step guide also there in preparation. It's not yet in that good state. The automotive workgroup part is much better because here's more domains. You really feel already the complexity in the step-by-step guide. And yeah, the binary parts also cause some headache, but we will come up during the next months with I guess so March, June timeframe, May, June timeframe, to have really a good documentation there that you can reproduce it. And especially about this system, there will be more in the Open Source Summit North America. And depending on this, CFP just closed, if we're lucky, there will be also something in the OSS Summit in Prague. And by this, I come to the end. And let's see if it works. My daughter asked if I was doing so many function animations, I should do another one for you. So let's see if this works. So here comes my hand and says a lot of thank you to all of you. And I'm open for questions. Clothing my notebook for today. Yeah. Mm-hmm. Yeah, you asked how to, so if we're using S-trace and if we analyze the process, how to determine which parts are relevant, which are not relevant, which belong to the workload? Yeah. So in the end, we can see from want to see which subsystems are involved first to see which are called quite often, which are used regularly. And you can also make the S-trace on application level, so that you can just say, here's the S-trace, this is my workload, I run it for a certain time, so you get a narrowed down scope. And in the end, all these commands which are become to a certain extent relevant, and we would like to just see, okay, where comes it, what calls what, where is the trace through the kernel, and how does these call map to different parts of our block diagram from our architecture. So we can say this has a higher responsibility, there's a strong likeliness to fail, and by this we would like to use it to understand the system and also to see in which subsystems do we go in, which source code is really used. So it's not that it's enough, it's just helping you, it's giving you a hint where to look at in all this mass of the Linux kernel. And we will throw out most likely a bunch of it. Yeah, it would say if we will not trace all or we do not trace everything, and we trust the system to a certain extent. This was the part which you're asking, and I can say it will be hardly possible to really go through everything in the Linux kernel in detail, but you can see that things are important, like from scheduling mechanism, that's something where you should look into memory mechanisms, and you try to find safety mechanisms on the highest level as possible. So try to avoid to go very deep inside the code, do any mechanism there, use it just for understanding how things work. And by this you cannot understand the full wide scope of the kernel. We had a very nice workshop in the beginning where Thomas Gleickson, I guess he was in there, and he said, oh, it could be a good idea to just draw an architectural diagram of the kernel. So you link all the modules, you draw the little boxes, and you see a lot of nodding faces from a safety perspective, from a safety processes perspective. And then he said, and if we print it in a very small font size, this diagram of the kernel, how things, we will fill not only this room, we'll fill much more, because it's enormous and you cannot handle this. And by this, I didn't mention it, but there's this STPA, System Theoretic Process Analysis. This looks on a dedicated perspective. So it just takes one perspective. If you think about an airport, you may look under for the firefighter lines, or for emergency exit, or just for the grocery shops for the luggage part, and you just say, this is my airport, so my system, and I take one element and see that this works, and then I increase the responsibility complexity by adding more things together and see if there are conflicts. Yeah. Further question?
What mechanisms are you using to try to look at which parts of the kernel get involved with the system call?
Parts are with this KSNAV and call tree, just to see how the system looks like, the graphical representation of it. But it shows you everything, and so we actually currently look quite a lot into source code directly and just browse through it. But there also the system tab part should come in, because system tab was used a lot also from us in the past to just see how are calls, how does it really go through this, and I guess this will give another benefit. So this workload tracing as Tracy scope, it just shows you what was called as a call. You have the navigation part to see it in a graphical representation, and then you really need to look into source code and click through source code.
Have you tried using ftrace?
Not yet. Not yet. It could be a good extension. Thanks. Yeah. Okay.
We're talking about the watchdog.
Yeah.
In order to, if there's, we'll just stop responding with resets, that's fine on IVR. Is that acceptable on the custom to reset?
A reset is never acceptable from a customer perspective. From a safety perspective, it would be acceptable, depending on how you argue. If it's a full system reset, it may not be acceptable. If it would be a flickering display for a short moment, it may be acceptable from a safety perspective. But in the 10 years which I had, every reset, every flickering which I could see in an infotainment system or in a cluster was not acceptable for going into production. Which shows you also that you get a drawing stability, system stability, boot speed requirements in there already in a very, very stabilized system. And then you have this just as a mechanism for safety, but from your design it should never be triggered. So that's in there, because it will not be acceptable from a user convenience perspective, and it will customer complaints. I guess my own IVI system crashed once after 7 years or something, or 6 years of having the car, and I was so happy to once see a reset in this system and say, okay, you cannot be still not 100% sure even after 100,000 kilometers of driving. It could happen that there's a weird situation which just causes the system to crash. And still on the other parts it never happened, right? So I couldn't see this at all. Yeah. Okay. We will have 1 or 2 more minutes for final questions. Otherwise, I also have some ELISA stickers with me if anyone would like to grab one. They're here at the desk. It's a good chance to approach me, even if you don't want to ask something directly. Cool, then, yeah. I say once more, thanks a lot. It was nice to speak here.